So the Ryzen 7 2700X is a high-performance desktop processor released by AMD as a part of a second lineup for Ryzen. This absolute unit of a CPU is built on the Zen Plus microarchitecture and offers significant improvements to its predecessor, the Ryzen 1700X. As you can see here, the Ryzen 7 2700X processor was released in 2017 till 2018 with a retail price of 1,300 ringgits or 329 USD. As you can see here, it comes with a socket of AM4, 8 cores and 16 threads, and it has a base clock of 3.7 gigahertz, but it also can boost up to So the Ryzen 7 2700X processor was released or first manufactured in 2017 across 2018 with a retail price of 1,300 ringgits or 329 USD. It's designed to deliver exceptional performance across a wide range of AP applications, making it well suited for gaming, content creating, and just overall heavy loads of work. As you can see here, it comes with an AM4 socket, 8 cores, 16 threads, and it has a base clock speed of 3.7 gigahertz, but it also can boost up to 4.3 gigahertz with Precision Boost 2 technology, which dynamically adjusts clock speed based on workload and the thermal space of the CPU. It has a total cache memory of 20 megabytes, a TDP of 105 watts, and 1x16 lane or 2x8 lane PCI version 3. And last but not least, it has a RAM compatibility of 2933 megahertz DDR4. So moving on to the series stack for the AMD Ryzen. Here we can see the Ryzen Desktop Gen 1, which is basically the predecessors of the Ryzen 7 2700X. We have the lowest, which is the Ryzen 3 1200, up to the, you can say, the newest from Gen 1, which is the Ryzen 7 1800X. If we move to the Ryzen 2000 series, which is basically the second series of the AMD Ryzen family CPU, we have the base, which is the Ryzen 3 2200G, moving up to the one that we were basically talking about, the Ryzen 7 2700X.
Like Ryzen employs what it is called a chiplet design, which, as you can see right here, it consists of 3 separate chips. These two are called CCX, and this one is called the IO die. Now, unlike Intel, which use one big die, Ryzen uses this chiplet design as a cost reduction measure. Right, so, moving on, we're going to have a look inside of one of these chiplet, which is also called a CCX. This is a general overview of the whole Ryzen CPU. You can see the two CCX consists of 4 separate cores. So each one CCX have 4 cores, 2 CCX 8 cores, and then it is linked by scalable data fabric, which what it does is connects both of the CCX into the IO hub. All of this, the thermal clock fuse, MUIO, MUX, USB, and memory control are built into this IO hub. Everything that you see, apart from the cores, are inside of here. Only cores are built into here and here. Right. This one is inside of each specific CCX. We have core 0, 1, 2, and 3. And all of these 4 cores shares all of this cache. We have 512K of L2 cache for each core, which means that there's 512 here, 512 here, here, and here, and all of this core can access each other's. Moving on, there is a 4 megabytes cluster, 4 megabyte cluster for each CCX, which means 8 megabyte per CCX.
Alright, so let's head to the next part. So the next part is called SMT. So what is SMT? It means a simultaneous multi-threading. So as you can see here, it starts from branch prediction and it goes into the ITLB. The ITLB means a look-aside buffer, and after it went from here, it goes into the instructions into the decode to bring the instructions into the micro op queue. And then from the micro op queue, we can see that it separates and branches into two sections, which is integer and also the floating point. So from here, you can see the integer, it goes into the integer rename first, and then into the schedulers, and then into the integer physical register files, where the instructions being executed by 4 arithmetic logic units. And also after this process, it will go into the 2 AGUs, and after this one, it will bring this into the 512K L2 cache. Alright, so the next one is the floating point. So the floating point, as you can see from the 2 branches, it will go to the first floating point rename and into the scheduler and into the FP register file. And here from the FP register file, you can see the instruction being moved into separate instruction, which is multiplier, add, multiplier, and add.
Okay, next we move on to the memory hierarchy. So memory hierarchy, what we must know about it is memory hierarchy is an arrangement of memory. Like we have seen, like this is cache. So it has several arrangement of cache, with this LO micro OP cache, L1I cache, L1D cache, L2 cache, L3 cache, and system DRAM. So first we go to L0 micro OP cache. So L0 is level 0 operational cache, which is, this is the specification, 2048 micro OP sideways set sensitive, you can see it, and then parity protected. Same with L1I in cache, which is level 1 instruction cache. So 64 kilo IP, 4-way set sensitive, 256 set, 64B line size, shared by 2 threads per core, and also parity protected. So if you can see, these 2 cache has parity protected. So what is it? So parity protected is basically one system to detect an error. How? By adding an extra bit into the data bit. It's called as parity bit. So this parity bit, if it like I said earlier, it will be inserted into the data byte. If it's same, then it's no error. But if it's the difference, then it means it has an error. But one fact that we must know is parity protected only scan, only detect the error but will not fix it. Move L1D cache, L1 data cache, level 1 data cache. So this is the specification: 32 kilo IB, 8-way set sensitive, 64 set, 64B line size, write back policy, 4 to 5 cycle latency for INT, 7 to 8 cycle latency for FP, SEC, DED, ECC. Okay, this is meant single error correction, double error detection. So sorry, I forgot to show this. So like for first level 0 micro OP cache, we can see it here, micro OP cache, and then level 1 instruction cache, this one, and then level 1 data cache, also this one. Okay, now move to the next one, level 2 cache. So this is the specification: 512 kilo IB at we set associative, 1024 set, 64B line size, write back policy, inclusive for level 1, latency 17 cycle latency, DEC, TED, ECC. Okay, so we have single error correction, double error detection. So this one is double error correction for this one, and then TED is triple error detection, means it's more advanced. And must I told that the more advanced you go, the bigger insights and slower in cache. Next we go to level 3 cache, victim cache, summit reach, Apple. This is also all the specification, shared across all core, 60-way set associative, 8192 sets, 60 bits line size, 14 cycle latency, same like the level 2 cache, just double error correction, triple error detection, ECC. And the last one is system DRAM. dynamic random access memory. This is main memory in the system memory hierarchy. So two channels per die average. This is specification also up to 128 gigabytes DDR4. This is the RAM, and then yes, 4 DRAMs device failure correction. So device failure correction is basically that it will correct any failure in the system, in the memory system. Okay, so this is what I'm gonna show you. Level 2 cache, we can see it right here. This is level 2 cache, and then level 3 cache, this is level 3 cache, and then system DRAM, this is 2, like it says 2 channels per die, so this is 2 channel. Alright, so that's it from me.
So to the next part, we will see how the processor works in real life. So as I open the task manager, we can see that the CPU have 16 boxes, which means 16 threads that have been explained by Ikmal, which one core have 2 threads. So AMD Ryzen 7 2700X 8 core have 8 core processor, so it have 16 threads. The next step, we will use sign batch, which a benchmark for CPU. We will run the sign batch in a multi-core. As we can see, it's slowly using all the thread or fully utilize the CPU to render an image. As you can see on the sign batch, there are 16 boxes of images that been produced because it have been utilized or being used by 16 threads or 8 core. So which makes the rendering of an image makes a bit faster. If we use a higher processor, will be more faster to render an image. Here you can see that the speed of the CPU that have been explained by Abdullah reached 3.7. It depends on the temperature and the workload that we use on the processor. So here's the image that have been produced by the 8 core or 16 thread by AMD Ryzen 7 2700X.